Hello and welcome to Anton Math. Now, we've talked in these last few videos, we've talked about propositions, both simple propositions, and then we talked about different connectives that we can use to turn simple propositions into complex propositions. And in this video, and the next couple of videos, I'm going to be talking about conditional statements or conditional propositions. And I have a little definition here for you. We say that if P and Q are propositions, then P, and then I have this, you see this little double arrow. I have kind of like an equal sign with an arrow on it, right? Double arrow. And it's read, I usually say implies, but P implies Q. It's a conditional statement. And you can also read it if P, then Q, right? So there's two ways you can read this. You can read this as P implies Q, or if P is true, then Q is true, right? P and Q both being propositions with well-defined true or false values. Now, for those of you who are looking into this course for computer science, you can kind of see almost right away the usefulness of understanding statements of this type, right? If-then statements are used very commonly in even the most basic of programs. Okay? Now we say P implies Q if and only if Q is true or P is false. Right? So when we're assigning a truth value to this proposition P implies Q, and we can see pretty clearly that this in itself is a proposition, right? If P and Q both have well-defined truth values, then based on this statement here, we can assign a truth value or a false value to P implies Q, right? So it itself is going to be a proposition. So I could actually write this, i.e. P implies Q is an equivalent proposition to P or not Q. Oh, no, I have that backwards, sorry. Q or not P. So let's use what we've learned about truth tables. Let's go ahead and set up a truth table for this. Let's say I have P, Q, and P implies Q. I want to know when P implies Q is true based on the true or false values of P and Q. So remember, we have two propositions here. It's going to be true, false twice, and then with Q I do true, true, false, false. This gives me all possible combinations of P and Q being true and false. Now P implies Q, we said that that's true if Q is true or if P is false. So first, these first two are going to be true, aren't they? I know that these first two are going to be true because Q is true. This third one, however, I have Q is false and P is true. So by my definition there above, P implies Q here is going to be false. And again, in this last one, I have that P is false. So from the second part of my definition, this is going to be true. Okay, so the proposition P implies Q, or if P then Q, this is true whenever both P and Q are true, or both false, or if P is false, no matter what Q is, right? And that one seems a little bit weird. Both of these are a little bit strange, aren't they? Just kind of looking at them. And I'll give you some examples. Once we get into proofs, mathematical proofs, we focus on this first line in particular, right? Notice that in this first line, because of this truth table, if I know that P is true, we're going to change colors. If I know that P is true and that P implies Q is true, notice that this only happens in one scenario, right? If I have P is true down here, P implies Q is false. Okay, so only in one scenario do I have both P is true and P implies Q is true. So from that, we can deduce that Q must be true. Okay, and we'll use this later once we get into methods of proof, but this is the basic idea behind proving something. We start with some proposition P that we know is true. We use some logic to show that P implies Q, and that gives us as a conclusion that Q is true. But I'm jumping ahead of myself a little bit. With this truth table, I want to go ahead and give some interesting conditional statements, and I have a couple of them here on this clear page. And actually, I want to keep this truth table up. So I am going to erase some of this. Hopefully you wrote that down, or you can rewind if you need that definition again or this kind of clarification. But what I'm really concerned with now is my truth table to verify some of these statements. Now I claim that these are all true, so let's take a look. The first one, if Tuesday is Thursday, then the sun is cake, right? This is an example of my fourth row down here, isn't it? I can have two false statements, and the conditional statement is true, right? So if P is false and Q is false, then P implies Q is true. And that's exactly what I'm saying here. This proposition at the top, this conditional proposition, if Tuesday is Thursday, is false, so no matter what I say here, this is going to be true. I can say anything I want, and this statement here is true. And this is a hard concept to get at first, to wrap your head around a little bit. You know, you have all these false things thrown at you, and then somebody says, well, wait, but this is true. And I know that seems a little confusing, but I'm not saying Tuesday is Thursday, and I'm not saying the sun is cake. But I am saying that this conditional statement is true. Okay? Like I said, we won't usually focus on conditional statements of this type, but I want to give an example. So this is row 4. This second statement, if 1 plus 1 equals 2, then the sun rises in the east. So this is what we'll typically be looking for in a conditional statement, right? P is Q implies Q is true, right? So this is an example of row 1 here on my truth table. And this last statement, if 1 plus 1 equals 1, then 1 plus 1 equals 2. Right? So this is an example of the second row right here, isn't it? If I start off with a false statement, the second statement can be true. But I could have equally put 1 plus 1 equals 3 here, isn't it? And I'd be back to my fourth row, or this top example. So if 1 plus 1 equals 1, which we know is false, then I can conclude, again, anything that I want to conclude. This is very important. Mathematical logic is based on principles and ideas that we assume to be true, like in this second one. And if this is true, then the second thing has to be true for the whole statement to be true. This is a very core concept to mathematical proofs and logic. Right? Now that's all I have with you on this conditional statement. I'm going to go over some examples in the next video of using this conditional statement, and go over particularly two things that kind of jump out of this conditional statement: the converse and the contrapositive. And these are two other statements that are very important, and we'll see you there.